Snezana. So I'm going to tell you some things that we've been looking at in the lab associated with interfaces that are relevant to a very common everyday process used by chemists referred to as solvent or liquid-liquid extraction. This is so common it's taught in undergraduate courses. If you imagine that you have some mixture of components that are dissolved in an aqueous phase, you can add some immiscible solvent on top and you shake it up and the components repartition. So it sounds very simple. Should be something we completely understand. Nevertheless, I'm going to spend the next 25 minutes or so telling you about it. So when I first started working in this field, about 12 years ago, I guess, I gave my first talk, and I had just spent a number of years learning how to use X-rays to investigate the ordering of molecules and ions at the interfaces between two immiscible liquids. And so I spent all of that talk discussing the way extractants, these small molecules here are extractants, they're dissolved in this organic phase. They're used when you extract metal ions, because basically to put a metal ion into a low permittivity phase, you want to neutralize it and shield its charge from the phase. So I had spent all the time talking about the ordering of these ions and extractants at that interface. And afterwards, one of the experienced veteran members of the community came up to me and he said, but you know, I thought the complexation always takes place in the aqueous phase. And I said, oh, no, no, no. And so in the last 12 years, the field has pretty much focused on studies of the interface and kind of ignored the aqueous phase in spite of what this senior person in the field thought at the time. However, his comment sort of lingered in my mind, and I've recently gone back to think about what is the effect of having complexation in the aqueous phase. And that occurs in many of these systems because these extractants, although they're heavily soluble in the organic phase, they're slightly soluble in the aqueous phase. So this process in which the extractants can go into the aqueous phase and complex with ions is something that happens. And the real question is, what are the consequences of that? So that's what I'm going to tell you about today. I'm going to be using an extractant, which I'll refer to as HDHP. It's a phosphoric acid extractant. It can be deprotonated and is charged, and that allows it to interact with these cationic metal ions. I've chosen this as the primary thing I'll be looking at because that's something that's used commercially, industrially for many processes. And one of the metrics in this community is what's known as the distribution coefficient. So you would take these two phases, you would put the extractant into the upper phase, say the ions are in the lower phase, you shake it up, and then you end up with a certain concentration of the ions you want in the upper phase, in the organic phase, and some remain behind in the aqueous phase. And a metric for how efficient this extraction has been is just to take the concentration of the ion that you're interested in, that's in the organic phase, divided by the concentration of that ion in the aqueous phase. So and that, of course, tells you how efficiently you moved ions from one to the other. So this well-known extractant has been studied for many years, and here I show some classic data from Sato from 1989, in which he showed that lanthanide, or rare earth ion like erbium, has a much larger distribution coefficient by about a factor 50 to 100 than neodymium. And this is generally true that for this extractant, heavier lanthanides are extracted much more efficiently than the lighter lanthanides. And so this extractant can be used to just separate heavy from light lanthanides. Now, in the experiments we do, it's useful to have a layer of extractants and ions in residence at the interface in order to probe their structure. These particular extractants transport relatively rapidly through the interface, and we had once tried some measurements and we realized that things were just moving quite rapidly through the interface. And so for these measurements that I'm going to show you for the next few slides, we've gotten rid of the organic phase. it turned out that the kind of measurements we relied on for what I'm going to show you actually don't depend on this. That is, I'm not actually going to show you measurements that show you the ordering. I'm just going to show you measurements that measure the ion density, that is the number of ions per square angstrom at this surface. So let's see what happens. If you take that water solution and you look at the surface, I'm not going to tell you about the X-ray measurements. This is referred to as X-rays. It's referred to as X-ray fluorescence near total reflection, which I'll just call it as X-ray surface fluorescence. And that allows you, so I'll be looking at here single types of ions, either neodymium or erbium. And so here I'm showing you the surface density, 10 in the units of 10 to the minus 3 ions per square angstrom. And the first thing you probably see is these pink columns here that show that the neodymium concentration at the surface increases greatly. That's as a function of pH. So this is for pH 2, pH 3, pH 4.5. That's not surprising because at pH 2, there are a lot of protons around which compete to bind with these extractants with the ions, and the ions lose. At pH 4.5, there are far fewer of those protons around, and the ions do the binding. So that's sort of a trivial thing here. The first thing that I notice when I look at this is that the neodymium is found at the interface to a much greater extent than the erbium for all of these pHs. So that was surprising because what we had in mind is that if we had an organic phase here, the ions would be extracted into the organic phase. Since the erbium is extracted much more efficiently, you should find it more often at the interface. Of course, we've taken the organic phase away, so maybe we've completely screwed things up. But anyway, I still had the idea that things that go to this surface in the water vapor situation would be more likely to be extracted when you had an organic phase. Even a little more surprising is that when you had these two ions compete with each other, so you had them both in the solution at the same time, the neodymium wins hands down. The erbium is completely excluded from the surface. So now we said, well, what if we created or used an extractant that just stays at the surface? So we don't have these competing bulk effects. So we use this other extractant. It has longer tails, which make it much less soluble in the water. The head group is exactly the same. So more or less the interactions with the ions are the same. And again, we mix neodymium and erbium together. And then we measure the surface density as a function of time. What you can see is, whoops, sorry about that. We put the, see if I can be a little more coordinated here. So we put this solution, everything together at 0 time here. And then at about 30 minutes later, after we've futzed around with aligning things and everything, we find that there's more or less an even number of erbium and neodymium ions at the interface. There's a little bit of separation. But shortly afterwards, you see that the erbium dominates. It goes to the surface. The neodymium goes down, goes away from the surface. And that happens in a relatively short period of time. So now we have a situation where the erbium, which is what is preferentially extracted, is now found at the surface. So this is exactly what we would expect, that the heavier lanthanide is preferentially absorbed. This is consistent with what is observed in industrial processes, but it does show that you will get the results of the industrial processes when the interfacial complexation dominates the process. So I'm not going to spend a lot of time following this up as to why the interfacial interactions will dominate the process in the commercial processes. But nevertheless, this shows an important point that if you have primarily complexation in the bulk, it's actually antagonistic to what you would expect to happen. If somehow you can make sure that things are happening primarily at the interface, then that is consistent with the kinds of things that people do in the industry. So despite the fact that this showed us that maybe the bulk effects are not that important. Nevertheless, we continued with this. And so now we take the same sort of system, but now we add the organic phase here. Well, one of the things we did a little bit differently is now we have a relatively high concentration of this extractant in the organic phase. And we did that because we were trying to mimic the industrial processes which use these larger concentrations. But you should keep in mind that you can put actually quite a bit more, a few molar of HDHP into the organic phase, but you can only put roughly 100 micromolar into the water phase. And that's where we did all those previous measurements. And so what we thought was going to happen is that by having a reservoir of this extractant, we would just achieve equilibrium faster in this lower phase. And so that's, yeah, because of osmosis, but that's not exactly what we saw. Instead, we saw these dynamical processes occurring. So there are a number of things to notice here. Maybe I'll show that to you again, if I can go back. First of all, this is a time-lapse movie that actually took an hour to measure. And one of the things you see is a lot of precipitation forming in this lower phase. So if that precipitation consists of HDHP, it means we're actually putting a lot of HDHP into the lower phase, much more than we would have expected. You see the formation of a second interface here, and then you see some dynamic processes and some instabilities at that interface. And then, of course, we looked at this for a wide range of conditions. So this one that I showed you here is basically this row here. So this is by time 10, 20, 30, 40, 50, 60 minutes. And then here we've just changed the concentration of the ion, the initial concentration in the lower phase. And you can see a variety of things happening here. There are instabilities at that second interface that's formed as a function of concentration. These features become coarser. If you go up to even larger concentration, the whole process is delayed substantially. And what I've shown you in this last column here is what you see 48 hours later. So a couple of days later, this is really the steady state where things have no longer changing. For all of these, there's precipitate at the bottom of the vial. It's hard to see here. You can begin to see it here, and then more here, and more and more and more. So at that point, we did some characterization of what is going on here, mostly chemical characterization, and let me tell you a little bit about that. Of course, the first thing is to ask, what is the precipitate? And so we did some X-ray absorption spectroscopy. I won't tell you about the details of these curves, but just suffice it to say that the precipitate consists of the extracted HDHP plus the ions, neodymium or gadolinium, depending on which we're using, and there may also be some water in there. These data are not quite accurate enough to really start to tell you everything we'd like to know, but anyway, they are consistent with complexes that are forming. Basically, where the ion, that's in yellow. I really don't like yellow against white, but anyway, that's what I've got. There's a yellow dot there, and that's bound to a series, according to these data, somewhere between 3 and 9 of these extractants. The other thing we were able to do is to follow the concentration dependence in different parts of the sample as the process was ongoing. And so we did that in a number of ways, 2 of which I'm showing you here. One is the brute force method of sticking a syringe in there, extracting a little bit of this liquid, and then going off to the lab and analyzing the ion content in there. The other way was to do this throughout the process by just sending in UV visible light and doing spectroscopy at these 3 positions. So we did this with a sample in which this was a fairly stable layer for some period of time. Eventually it does destabilize, but it's a little more stable than what I showed you for for the previous slide. In the previous slide, I was using pH 4.5. This is pH 3.0, which slows things down a bit. And so what you see is when you measure right above the interface, that you immediately see that neodymium is being transferred from the lower phase into the organic phase. And that's good. That's the whole purpose of the process. It happens quite fast. You can imagine something in which these extractants go to the interface, grab onto these ions, and pull them into the organic phase. You can also see that throughout the entire water sample, water part of the sample, not just what is a relatively pure water phase here, plus also this kind of precipitation region here, throughout that entire region, you see a very quick extraction of ions. So the first data points here basically measured roughly a minute after this sample is put together. So even though this distance is about a centimeter, you're already within a minute or so starting to change the ion concentration down here. And then you see something similar in this region, just you're removing ions to a greater extent there. So that picture more or less leads us to the idea that we have immediately ions being brought into the organic phase. Then we have some period of time, depending upon the initial concentration, in which you form something else going on here, a second interface. And then that second interface also destabilizes. One of the questions we were interested in was, why is this whole process being delayed as you go to higher concentration? So here's a kind of a simple MD simulation, simple in the sense that it doesn't show the extraction into the organic phase, but because we biased things a little bit to try to get the extractants to go into the water phase on a reasonable time scale. And so when you have a lot of ions around, basically the ions, at least this is what this suggests, is that the ions are complexing with all the HDHP as it's coming in from the organic phase. So it's basically sort of blocking the interface. And that, of course, the HDHP will draw the ions away, and eventually you get to a low enough concentration that you start to form holes in that interface, which allow HDHP to go through. So when you have a lot of ions in here, you basically block the entire process of bringing HDHP into the lower phase. Down here, that happens very rapidly because the initial ion concentration is low enough. To get a little better look at what that second interface is, we made a 2D slab of liquids in a microscope slide arrangement, and then we looked more closely at that. So I know it's a little bit difficult to see this. I don't know, I'm hoping you guys can see it. I don't know, can you see these little black dots here and little black dots here and little black dots there? Yes? Okay, so what we see here is that a precipitation front appears, but separated from the main liquid-liquid interface by a depletion region where you don't see anything. And then, so you can imagine there's some flux of HDHP coming down here, probably complexes of HDHP and neodymium forming in this region, but then at some point you start forming precipitate. So perhaps that's due to some fluctuations towards supersaturation in that region. It's not clear to me exactly what the mechanism is, but that's one of the things we still need to follow up on. But what is odd, which struck us, is that you sort of have a conduit for bringing HDHP into the aqueous phase and then taking it out of the aqueous phase by the precipitation. This is no longer in equilibrium. It's not going to dissolve back into the aqueous phase if you waited a long time. So that allows you to move a lot of HDHP into the lower phase, which is not what you want to do in this process. That's not what the people who are doing this commercially want to do. They would prefer that it not be in the water phase at all. So that's now part of the new process. And then eventually this second interface is what becomes unstable, to have some of the Rayleigh-Taylor instabilities I showed you in the previous slides. Now, the real kicker here is that that depletion layer actually controls the whole process in a very strange way. Because this precipitate that's formed is actually soluble in the organic phase. So if you hadn't separated it by the depletion layer initially, it would never form. It would just do whatever aggregation it wanted to do at the interface, which would just dissolve into the organic phase. So here I've shown you two examples of this. These are slightly different compositions. So these are both samples that have been sitting for many, many hours. This is a sample where the precipitate has settled down, but it's very loose and fluffy. And it fluctuates around. And at some point, it fluctuates such that the top of it touches the organic phase or touches the interface. At that point, well, let me just show you the movie. You can see it over to the right here. At that point, the precipitate just disappears. It just dissolves into the upper phase. This one here is similar, but it's not so fluffy and there's not as much of it. So in order to get it to come up and touch the interface, my postdoc had to shake the bottle. Like he had to shake it twice. So this movie, unfortunately, needs to be slowed down. But anyway, you can see it. You can see what's going on here. Here he shook it, and then eventually it rises and just disappears. On the time scale of this movie, it just goes away.
It's just different metals, right?
They're different metals, right? That's the primary difference. This situation at pH 3 gadolinium looks a lot more like what I showed you originally, the pH 4.5 erbium. Well, the gadolinium is different in size from the neodymium, so they have different electric fields, and they have different, the neodymium will be less strongly bound to the extractant. So this is, just to summarize, sort of very crudely, we've shown some experiments to really suggest strongly, not quite prove, but suggest strongly that it's really complexation at the interface which is important. So my two colleagues in the audience here are thinking, yeah, so what? But it is a question as to what happens when you have complexation in the aqueous phase. And if you do, you're in trouble. Because then the strong interactions that control the extraction at the interface into the organic phase now control binding into structures in the bulk phase, which is not what you want. And then we also show that as a result of those structures that form in the water, there's all sorts of stuff going on. Complex reactions and transport phenomena. Yeah, and there are convection cells there. That's right.
Convection cells.
Yeah.
Do you see them on the surface, convection cells?
No, we weren't able to see them on the surface. They might be there, but we didn't turn the camera that way. Yeah, I don't know if you remember the movie, but you can see them rotating. Yeah. Yeah. So just remembering the people who did the work. This work was really done largely by a postdoc of mine, Pan Sun, who is now a postdoc at Oak Ridge National Lab, very talented and creative guy. And in addition, there was X-ray work here, which was done at NSF's ChemMat cars, which is an NSF-supported facility at a DOE lab, the Advanced Photon Source, and Wei Bu and Pinhua Lin played an important role there. And Alex Brown, Art Gellis, and Alon Benjamin have played roles in my work in other situations, though not really for this work. Thanks very much.
So questions? Yes.
So very exciting. I thought that the vortexing and all the fluid dynamics thing was really, really neat. I don't know, are you familiar at all with cloud point extraction, Mark?
A little bit.
Do they observe similar types of fluid dynamic phenomena in cloud point extraction? I was trying to rack my head because it would seem like you should see similar stuff, right? To not the second precipitation front, but the dynamic. Like I was really amazed actually at how fast the precipitates went back up into the organic phase.
Well, it's more like 30 seconds, right?
But still, that's definitely fast. Would you say that's faster than diffusion?
Yes.
Yes.
A lot of things going on here are faster than diffusion, right?
Yes.
I mean, you have a sample which is a centimeter high, you start the extraction at the interface and you see the extraction.
Sure. But
So that's
but normally when you think of precipitation phenomena, right? Like, and there's a big gap, like if it's settling on the bottom and then all of a sudden there's like some, small bits of it go into the organic phase, right? So I'm just kind of curious in the context of like these ideas of like convection and the fluid dynamics of the aqueous phase, if there's anything similar in cloud point extraction.
Not that I'm aware of.
Yeah, because that was cool. Yeah.
Okay. Other questions?
A very interesting talk there. I'm wondering about how the difference in the metal plays a role in your
How the
study.
difference
In the metal species.
Oh, in the metal species?
Yes. Maybe that complexation equilibrium may be different. Do you have some idea?
So, I mean, this is probably not telling you anything you don't know, but so for example, this is a potential amine force free energy curve for neodymium and erbium in the bulk water. And so, as you would expect, the erbium has a deeper well here. It's a smaller ion, the electric field is stronger, and so these effects are playing a role. One of the first things that you expect to see, of course, is that for the first part of my talk, for example, is that since the erbium interacts more strongly with the extractant, it should go to the interface if there are amphiphiles at the interface. But the one thing we don't understand is that although most of this follows a trend of erbium interacting more strongly with everything, it seems to prefer to form these structures in the bulk. So if you have the ability for the extractant to go into the bulk, the erbium will go there rather than at the interface. You might have thought naively that it'll just go wherever the extractants are, preferably. So when we published this work, I explained it a little bit differently in the publication because I had a different point of view here. And that is, there I said instead of the neodymium dominating the surface, it was that the erbium dominated the bulk structures. But there is this open question, I think, as to why those particular bulk structures are more strongly stabilized. And so that's relevant for the second half of the talk as well.
What's the difference in the creativity of hydration for those 2 ions?
Yeah, it's substantial, but I don't remember the numbers, I'm sorry.
So that could explain some of the preferential behavior, right? Because if erbium doesn't want to lose any waters of solvation.
Yeah, it's less likely to lose its waters of salvation. Yeah.
If it would be, for instance, other questions? Virtual participants, maybe someone has questions?
Yeah, Mark, this is Ben Dowdy.
Hi, Ben.
Yeah, really nice talk. I was wondering when you were explaining this blockade of these ligands at the surface, would that blockade not play a role in stopping the transport back through the interface?
Let me just so everybody else knows what. So you're asking if the blockade could prevent the ions from going into the organic phase?
Yeah, like I understand this is something that over a long enough time, it's all going to separate itself back out. But do you get the impression that this blockade, it's blockading the ligands from going into the aqueous phase, but also it's blocking the ions from transporting back into the organic phase?
Yeah.
So I was wondering, do you see a delay in maybe what's extracted into the organic phase versus what's extracted into the aqueous phase?
So yeah, this is a slightly different sort of sample, but I think there's no obvious delay, let's put it that way. And the extraction into the oil phase is quite fast. So there are 2 curves here. They're measured in these 2 different ways. And this is a very steep slope. It's occurring almost immediately. So I think the issue here is that you have the extractant coming from the organic phase to the interface, it can interact with ions and pull back into the organic phase. So that blockade is not really blocking it from going to the interface and coming back. But it is blocking the HDHP from going into the water phase, basically forming a barrier there.
Okay, that makes sense. Thank you.
I think it's asymmetrical in that sense.
Other questions? If it would be, so what would your expectations would be if it would be, say, different atoms, like, you know, not, would it be any change qualitative in behavior and how significant it may be? So essentially it looks like that the results of the experiment are quite sensitive to what specific material, right, is being used, like, you know, what specific ion.
Well, that's true. I mean, you know, it's known in, you know, in the practical solvent extraction world that there are these differences between materials. But I should say, you know, in all honesty, what solvent extraction people do is they shake things up. And so to the extent that, you know, what happens with these results when you start shaking things up is a little less clear. One of the things you do form when you shake things up is you form emulsions. And so we actually did a little experiment here to see what happens if you made kind of two pseudo drops. So this is like oil, and this is oil, and so this is like the interaction between two drops. And you know, you see these precipitates form, but of course, if you're going to shake them up, you're going to destroy this depletion layer, and they're going to redissolve. And I don't know whether this will have any practical impact on the way people separate ions is a little bit less clear to me.
I see. And what is the size of this container? Like, you know, say centimeters?
Yeah, millimeters.
Millimeters?
This is millimeters. The other containers are basically centimeter by centimeter kind of sizes.
And what about like surface tension effects in this case?
Like what kind of effects?
Capillary, because if it's a millimeter, it's a one with the...
Well, you can see that, you know, the interfaces are curved. We might. If we had some good simulations.
So interface experiments in nature and are even more exciting than we used to think. So let us applaud our speakers. Thank you so much. Yes, and we will proceed to the next presentation.